Good afternoon, everyone, and welcome to this webinar on CAx Automation. So we'll directly jump in the topic. So basically, in this, we are going to focus on how do you use CAx Automation effectively, and what could be opportunities for automation, as it was mentioned in the introductory post that you might have seen and against which you had registered. So let's move to let's get into the presentation. Let's quickly start with an agenda. So in this, we'll basically cover about 5 broad topics. We'll go over introduction, where we'll actually talk a little bit about why we automate, what are different drivers for automation, and what you can achieve from automation. Second section, we are going to talk about automation approaches. So these are the ideas which we have evolved over the years when we have been going through different kind of automations. Then we'll talk about case studies. So with Prescient's experience, we have many case studies available in our repository. We have picked only 5 or 6 case studies, which you will be able to relate with the automation approaches we are talking about. Now, when you talk about automation, the biggest challenge is how do you adopt automation? So we have put some kind of framework or certain, what I will say, plan, how you can automate, what are different technology options for automation. We'll talk about that. And finally, we'll summarize and the question and answer. So the question and answer on any slide, if you have a question, just put it on the chat box. But we'll take it at end so that we are able to cover the complete topic and do proper justice to it. Okay, so with that, we'll get into the details of actual content. So let's start with introduction. Here we are going to talk about a little bit about background. So as when we look at automations, we all know, like engineering organizations, you may be working in many different functions as part of your engineering. So everybody uses these CAD, CAM, CAE, which we are calling as CAx tools for product definition, validation, manufacturing planning, and many such applications. So basically, this is all about defining your product in 3D, and then using it for various downstream things like validation, how do you manufacture it, all the planning, so on and so forth. So there's no doubt, like if we compare very old days when things were happening on paper, compared to that, we have achieved a lot when we adopted these CX tools. But as we know, the product complexities are growing and there is more demand to do things much faster. And hence, engineers look at automations to raise to the productivity and also the quality. And this comes in 2 parts. For example, like this comes in 2 different ways. You have this CX tools at center. So one driver or one way of looking at it is like your ISV or reseller from whom you basically got this particular software. They keep coming with new modules, best practices, and they keep updating you about those. And then you decide to adopt certain things. So as part of best practices, there may be certain inbuilt automation or some new modules which are going to raise your productivity. So I would say this more as a push coming from your software vendor. The second thing that comes from actual users. So users who are working on this day in and day out, they typically identify certain needs. And that I will say more as a pull. So they say like, I spend so much time on certain activity. And if I have an automation for this, that would be helpful. So that's why I would say this as a pull. So this is how typically the automations implementation take place. But these initiatives basically face multiple challenges. Very first challenge is like sometimes you don't. The challenge is how do you find the automation opportunities. In some cases, you may have so many opportunities that you will have to figure out like how do you prioritize those opportunities. And finally, the budgets are limited, so you'll always have to prioritize and get reasonable ROI. We cannot automate for the sake of automation. We have to basically prove it with a proper ROI. Second thing is more, I would say, related to engineering IT functions who develop actual automation. For them, the right technology or solution for the automation. Because when you look at automation, there could be many ways you can automate certain things. And I'll actually give some example through case studies when we are talking about it. So how do you choose the technology or solution for the long-term evolution? So though this decision falls more in the engineering IT purview, but as an engineering user, you also have a lot of stakes in that, because the engineering users need to basically get the derive those benefits on a continuous basis. And the third thing is like holistic view on automations for next level improvement. So what we have seen is like often the automations are implemented and then they hit a roadblock or a dead end because you are not able to improve it further and not able to get next level of productivity improvement. So these are three challenges, broad challenges, I would say. And we are trying to present a solution for those. So while we go in details, I would like to set a little bit of stage talking about Prescient, just to give you background, like where we are coming from, what experience we have gained. So Prescient is in CAD domain for 25 years in various capacity and closely associated with engineering and software community. So just to give you an idea, like our founders come with 30 plus years experience, and they actually started as engineering users when the world was doing many things on paper. So they have seen all evolution. Everybody has seen, but they have seen that much deeper. And over the years, we have been associated with the full ecosystem of the CAx vendors, that is ISVs, and also engineering users. So broadly, we have four types of associations, which actually give us much better view of the whole ecosystem. So for the ISVs, we are development partner, where some of our people actually work inside those development teams and do the development. So they have much deeper insight in like how the softwares are evolving. Second is like we have our own technologies, which again go and integrate in with these CAD softwares. So that gives us another view of the whole ecosystem. Third is like our engineers actually work on various engineering projects where they get uh, good insight, like get user insight, like what is required, what is not required, what are challenges. And then finally, what we are presenting through automation, that is important aspect where we have implemented multiple automations and seen the whole life cycle. So that gives us a clear idea like what is required, what challenges the automations face. Through these years, we have touched various engineering functions like product engineering, where the actual product definition takes place, the manufacturing engineering, manufacturing planning, inspection, support, and many such activities we have seen. So that broadens our overall perspective, not just related to CAD, but even various facets of the overall CAx ecosystem. And we have provided solutions for various domains like automotive, aerospace, heavy engineering, process industry. So with that, actually, we have gained much broader view of where things are going, how they are required. So with that, let's look at few opportunities which we have identified. So basically these opportunities, I mean, obviously you are aware of a lot of opportunities, but we have just tried to list based on our experience. So typically we have seen like 10 to 15% of effort, the engineering effort, go for quality checking and correction. So this everybody would agree. Uh, but again, despite of that, there are change requests, and so, I mean, some of these, like 25 to 30% of these, are actually because of design error. So that, despite of putting 10-15%, it leaves a lot for eliminating those design errors. The third thing is like 40 to 60% of engineering effort add value to final product. Now, this might be surprising statement for engineers who are working day in and day out, like how that is possible. But if you really look at like what is happening through product development, we are basically defining a product, and then there are a lot of support processes that need to happen. So when we are saying this 40 to 60%, we are basically attributing like the time that is spent on that product definition or product validation, planning, etc. and a lesser part on the derivatives like documentation, so on and so forth. The next is 20 to 30% of effort goes on reporting, recreation of information. So this is what I basically talked about the earlier point. You go through a lot of tools and end up creating that same information. For example, you have CAD where you know, like let's say what kind of loads would be there, because considering those you would have designed these. But when you take that model in CAE, again you will have to recreate that information in some different form to apply the loads on your CAE model. So that is the effort, which probably is which is again an opportunity. And the next thing is like 40 to 60% of lead time engineering jobs spent in waiting. Again, this could be might be a surprising statement for many of you. But if you look at it, as engineers, everybody is are busy working on multiple things. And if you look at actual engineering job, it is basically you are working on it for a certain time, then you hand it over to next step, and the next person may not be ready to take it immediately. And that is the waiting time we are talking about. So which amounts to about 40 to 60% of overall lead time. And the last one is like engineers put 60 to 80% of effort in design edit. So now the opportunity we see here is like very often when you look at automations, these automations are implemented considering like you are going to create things from scratch. But if you are putting 60 to 80% of effort in edit, like reusing existing design, if we identify and accept that, acknowledge that rather, then we would be able to get much better automation, plan the automation in much better manner so that you can use it for the complete life cycle. So with these opportunities, let's see what kind of, let's say we address these opportunities, and then we'll see like what kind of outcomes we can expect from automation. So here we have basically, we are trying to put four different facets. So very first obviously is about quality. So we all know like quality is the primary thing. And when we started, we obviously talked about it. Like quality is one of the main drivers. So we'll not go in a lot of details. Everybody would agree with that. Second thing, of course, is cost, where your engineering effort on modeling, development, detailing, if you reduce these costs, that obviously is a benefit of automation. Another interesting thing is like if through automation, if you can eliminate any special hardware or any software license, that also would be beneficial. That also would translate into cost saving. The next is delivery time. So for everyone, we always talk about this quality and cost, but we miss the but the time pressure is actually increasing day by day. So the idea here is like when you have automations, you would be able to shorten your development cycle and make it more predictable. And how we'll actually talk about that. And second thing would be faster change response, where those ECOs or any change requests that keep coming, you should be able to how quickly you are able to respond to that. That is going to define your overall lead time. So that is where this aspect would be helpful. And then the last one is innovation. So I would put it in two different buckets. First is like, you are actually freeing the engineers from the mundane task, and that way you are giving them more bandwidth to explore design options, think innovatively, do some creative work. So that is one aspect of innovation benefit. And second is enable innovative digital process. So I have one case study which actually talks about it, which will give us a better idea like what this would be about. Okay, so this gives us an idea about like why we automate, what could be opportunities, what benefit we can expect. So with this, we'll move to next subtopic, which is automation approaches. So before going into this, I would like to set some stage. So as I had mentioned, like we have worked on this whole ecosystem for so many years. And with that experience, basically, we have evolved these approaches, or I can also call it ideas. I would refrain calling these as principles, because some of these are, a little common sense based, not something like very theoretical basis. And hence, we are just calling it either approaches or ideas. So let's take a quick summary of what approaches we are talking about. So very first is whenever we want to approach automation, we should cover complete process. So when I say cover complete process, at least we should understand and touch the complete process. And we'll talk about like what could be benefit of doing that. Second is understand connectivity. So in the design process, as it is represented in this picture, basically there is this physical design, and then there are many concurrent processes happening around that. There is analysis, manufacturing planning, tool design, process planning, etc. So while these things are happening concurrently, there is a lot of data exchange that happens. And as I had mentioned on our opportunities, there is a lot of recreation that happens. The information exists, say, in physical design, but again, you end up recreating that in analysis or in tool design. So if we understand connectivity, we should be able to leverage that and reduce that particular effort. The third is front load validation. So we'll again talk a little more about this. But the idea here is like the more you delay the validation, you are going to get longer iterations of your product development. So how to address that? We'll talk about that aspect. The next one is capture users intent. So this is like again, providing features or representation that matches with like how the engineers are thinking. So that is the next one. The fifth one is more interesting. Like how do you utilize the waiting time? So we talked about that idle time, the waiting time. So how do you utilize that? And that can help us speed up our overall development cycle. And then there are two topics which are actually related to implementation, which is like how do you pick between simple versus complex automation, and some kind of comparison between single click automation versus toolbox. So these two topics always come when we discuss with any engineering users, and hence I thought I'll touch upon these topics as well. So this was an overview. With this, let's go in little detail. So very first, we'll talk about cover complete process. So the idea here is to understand and map complete process. So on earlier slide, we saw product development going through so many stages. The idea here would be like if you understand that whole process better, you would be able to find automation opportunities in much better way. Of course, as part of your function, you may not have control on the complete process, so it is not always possible. But at least wherever you have control, you should understand and capture that part of process, and also you should try to understand what is happening upstream and downstream, so that you will be able to connect things better. Now, when you capture the complete process, there are multiple things you can actually do. Very first, which I think most of us are familiar, but I'm just putting it for the record, which is like doing some kind of value stream analysis. So, as we on earlier slide, there is only certain effort which is like value added, and then there would be certain effort which is required as part of process, which we are calling as non-value add but required, and eventually there would be certain effort which would be non-value. So this the kind of you can actually achieve this even before going in automation. When you look at activities, and if you do this kind of mapping, that itself would be your first win when you are trying to do this exercise. The second thing is like when you capture the complete process, you would be able to identify certain bottlenecks. So here I have done just a schematic representation, but if you try to understand like how much time each process is taking, you will obviously see certain bottlenecks, and these are going to be good candidates to improve throughput. So let's say at these bottleneck points, you decide to apply automation, it is going to improve your overall turnaround time. So that is another possible opportunity that you can leverage when you understand complete process. And the last one is interesting when you actually look at automation. So very often in your process, you'll find like there are many small tasks which are automation candidates, but if you try to automate them one by one, they are not going to help so much. So the idea here could be like if you group those tasks, automation tasks, and then automate in one go, that is going to give you the real benefit. For example, here you will see like on the top bar, there are four different automation points, let's say opportunities, tasks, which you have identified, but they are so small that automating one by one is not going to help you. If you have a possibility of rearranging those and let's say bring them sequentially one after another and then do the automation, so that is going to help you much better. So these are three things which you can potentially do when you understand or when you have a good view of the complete process. So once you capture the complete process, the next thing, logical thing would be like, how do you understand the connectivity? We talked about this topic a little bit when we on that picture, but let's understand it a little more. So if you look at any, say, product definition, this whole journey goes through multiple functions and multiple tools. So just I have created a simple representation where it starts with some kind of engineering definition, then it goes to physical definition where you do actual design, and then manufacturing definition where you decide like how this would be manufactured. Then also you have analysis and verification, which for simplicity I am saying like it would happen in parallel. It may or may not be. And finally, when you have the full design and manufacturing plan ready, you also need to plan for the inspection and testing. And for this, there could be many different aspects of the same model which are useful. So let's try to understand it with a good example. So let's consider like you are designing an electrical circuit. So engineering definition is where you would basically define those circuitry and even possibly details of each individual component. In physical design, it is more about routing and bundling, because the circuit diagram that we put on the first stage is not, you need to figure out like how you are going to uh, route those wires, how those wires are going to flow to finally achieve whatever that circuit is supposed to achieve. So that is your second stage. The third, when it comes to manufacturing, you actually need to figure out like how that form board with which those wires would be assembled and that harness would be created. So that form board mounting need to be defined. So that again depends on like certain earlier steps. Then your analysis of that circuit, where the important thing is like in first when you were defining that electrical circuit, you had obviously done certain analysis, but finally you also need to understand like if the wires are going longer, then there would be more voltage drop, and how do I address that, or how do I reduce that? So for that you need final analysis, which is based on your wire sizes, length, which would be critical at this stage. And finally, when it comes to inspection or testing, for example, you need to understand correctness of routing, and also you need to check quality of all joints to ensure that there are no loose ends, so etc. So if you see, there is a single design on which all these things are operating, but because the functions are different and possibly their tools are different, it is very likely that you will end up creating a lot of information again and again. So if you understand this connectivity between functions, and if you find ways to preserve this connectivity or build ways to regenerate this correspondence, it could be by any means. For example, there may be certain wire IDs with which you can connect the things. There may be, you might be able to connect certain things purely based on position. For example, if it is a something like rivet, then a rivet joint, then based on position, you might be able to connect certain things. So there are many different ways with which you can actually build this correspondence, and then basically recreate certain information automatically rather than putting all those details manually. So this is the first benefit, like if you preserve that connectivity. Second benefit that we have seen is like it is going to help you faster impact analysis and change propagation, and also feedback correlation. So very often what happens is like we only consider like there would be electrical circuit, how it will translate into physical design, and so and then to the further steps. But consider like in analysis, there was some issue found in certain wire, and now you want to go back to your engineering definition. So if you have lost that connectivity, it becomes very difficult. Or I mean, you need to have a lot of discussion on, like for example, which wire is that or which component is that. So if that is if we are able to represent it correctly, even this is going to help you. If that connectivity is preserved or you are able to regenerate it properly. Okay, so that is another idea when we talk about automation. The next one is about validations. So validations are any always part of any design cycle that we talk about, and most of the time the validations end up happening at end, and then they basically create much bigger iteration. So the idea here is to bring checks or validations earlier in the process to shorten your design iteration. And this could be done by building some simple or approximate checks for schematic design as early indicator. So why validation basically happen at end? Typically, let's say you want to do a CAE analysis. The CAE analysis cannot be done unless you have full product definition available. Same could be for the circuit. Like unless you have the actual wire lengths available, you won't be able to do that voltage drop analysis. So there are certain blockers or challenges with that. But we'll share certain ideas like how this can be done. And let's take that with an example. So let's say we want to so we basically propose three different stages which can be considered here. Take that with an example, like we want to do calculate area of an irregular shape. So as we know, like there is certain accurate calculation which can happen through actual integration or some numerical calculations, etc. The second thing is some kind of approximation where we do triangles and then sum of area of triangles that could give us second level. This may not be as accurate as the first one, but this could be faster. And the third one is very simple, which we had learned when we started when we were in school. Like take a graph paper. On that you can basically draw the shape and then do count areas, count the squares which are completely covered, count squares which are partially covered, and then do some approximation. So the idea is like, can we extend this kind of analogy to any check or any validation that is being done? And if this is not clear, we have an example which actually explains how this was done. And the idea is like, if you integrate these checks in as part of your process in form of in-process checking or mistake proofing, that is going to help you shorten that design cycle. By no means this is going to replace your actual validation, but the idea here is like the early check, these checks can be based on a premise that it is better to be roughly right than absolutely wrong. So let's say you are able to pass that design which is roughly correct, not rather if you are able to eliminate certain design options which are going to be completely wrong, that also is going to help you reduce that iteration. So that is the idea, that is the premise which we are proposing here. The next one is more related to CAD, but I think you all would be able to correlate with this. So when we look at any CAD system, it provides features for basic geometry creation like extrude, revolve, cut. They are all when we use any CAD system. Basically, these are the first things which we learn. And then there are some specialized modules which provide specific features. Like if you are doing plastic design or casting, then there would be ribs or bosses. If you are and stiffeners, if you are working with sheet metal, there could be features like joggle. So when we so basically with this, the systems are trying to get closer to your actual design, but your design domain might be much more complex and it needs to be expressed in much higher level or in form of a composite feature. For example, here I have put a picture of one complex hole which has so many features. If you want to create this particular hole in your 3D geometry, it will take so many features. But when we while implementing, if this is created as a feature template with very minimal inputs, like for example, this composite hole with single point, center line, and then the dimensional parameters. So if you have this kind of feature available, it becomes much easier for the user to create that feature. And then they are able to they get a feature that basically has inputs and controls that are aligned to their domain level. So these dimensions, everything typically they get as input in their from the upstream, and they would be able to create this feature very quickly rather than breaking it down like, okay, here I will apply fillet and all that. And secondly, having this kind of feature is also going to bring the consistency. So this kind of feature, it eases feature creation and also eases change propagation. For example, as part of their change, they need to change certain dimensions. So they don't have to go back and understand the whole, how that feature, how this particular hole was built. Instead, they know like this is a template, this is the dimension I need to modify. They will modify it and they will get the result. So that change propagation becomes much easier. Uh, so this is about having some kind of higher level features. Then next point that we are going to talk about is more about a broad process level, where we are saying how to utilize the waiting time. So I'll explain it with a premise. So we already looked at the point like the designs are waiting 60% of the development cycle. And this is not like the people are idle. It is about the time between the things are taken care. And when we are saying 60%, we have actually counted a lot of idle time which we don't realize. For example, what happens overnight, that also is an ideal time, idle time per se, right? So I have tried to represent it here with a feature. For example, with a schematic. So for example, there is 3D definition and then there is a dotted line which shows idle time and then it gets picked for simulation. So this is the idle time we are talking about. While the job is idle, we also need to look at the aspect like your CX tools and IT resources, which is also a heavy investment from your side. That also might be idle overnight or over the weekends. So can we use these two things and do something about it? So that is the overall premise. So we want to utilize idle time to shorten the cycle. And there are already some existing cases where this happens. For example, when you have a PLM, typically the PLM has certain modules which allow you to do some kind of DMU simulation for contact or clash. So typically this happens in a waiting time when or it might happen overnight as a scheduled job. Similarly, there could be wait and balance evaluation. So this again happens in the idle time. We are saying like, can this idea be extended to more opportunities like meshing or the CAE run, then CAM toolpath or kinematic synthesis, and there could be many such things. And if we do that, then it is going to actually help in two ways. One is like your IT resources, the tools are utilized, and the engineer's time is also saved. So we have a concept on this, which we'll present in the case study. Uh, and then, so these were ideas about actual automation opportunities. The next one I have put under miscellaneous. There are two topics which basically come to table when we are looking at actual implementation. So very first is the question like which automation you should pick, like whether you should go for simple versus complex automation. So very often we have seen like people, I mean, there is a preference like something complex. If I do, I would be able to prove something like, okay, this is what we have done. I would be able to showcase it better. But there are pros and cons of both approaches. For example, if you try to automate simpler tasks, what we have observed is like they are more frequent, and hence you would be able to as they are simpler, you would be able to automate them at a faster and much lower cost. And secondly, because they are frequent, the time saving is going to turn into a faster ROI. So this is one side of it. If you look at complex tasks, they are they are less frequent, and hence basically they are higher cost for automation and slower ROI. Of course, there would be certain genuine cases where you still need to go for a complex automation. But given a choice, we would always basically we advise to go for simpler tasks first, because finally we have to prove the ROI. That is the point we want to make eventually. So what we typically advise is automate simpler tasks and free the users to take care of complex tasks. This way, we are able to move the automation things much better. Second question that often comes is like single click versus some kind of toolbox or wizard like approach. So basically what happens when we talk with users, they typically think if something is being automated, it should be just a single click. I give certain input and then I should just get the output. So we have seen like this is difficult to implement, but more importantly, whenever we implemented this kind of automation and it went into actual usage, we figured out like for users it is difficult to visualize and provide all correct inputs in one go. For example, one case we automated one process which runs overnight, and there were about 100 odd inputs which the user had to provide. So very first this looked very attractive, but after implementing after actual usage started, the engineers started realizing like if they miss even one parameter, they will have to rerun that whole overnight, they will have to take a full run of that overnight job, and that actually slowed down their process. So there are certain cases where this can happen, so we just need to be aware of that. uh, Second approach is more alternative to that is like which is toolbox or wizard like approach, where instead of doing a single click automation, look at the process and identify multiple utility automation. So the utility could be multi-purpose typically, and they could be simpler to implement. So this kind of approach gives more control to the user. Of course, the engineers need to do certain things manually, but in our observation, this helps the engineer much better, because then you can implement one utility at a time, go on implementing and add benefits on that. So if you ask me, I would prefer toolbox or wizard kind of approach rather than single click. But of course, we have certain evolutions, and I am trying to present those in the auto adoption framework, where we can start with simpler things and we can actually go to more complex things. So it's not like we are completely ruling out complex. We are just suggesting certain comparative assessment of that. So these are basically different approaches which we had listed out so far. But let's try to relate those with actual case study, so that you'll be able to get a better idea. And because it is always important to see the real life examples rather than talk certain theoretical concepts. So as I mentioned, we have picked like 4 case studies. So these case studies are picked on the basis of the correlation with the principle, with the ideas or approaches we talked about. And I would again reiterate, we have so many more case studies, but we are refraining from putting those, because otherwise it would become just a case study presentation, which we want to avoid. So very first is about sheet metal part merging. So basically the idea here is like there is an existing engineering process where the engineers, the more manufacturing side engineers, they analyze complex sheet metal assemblies, and their task was to merge sheet metal part to create less number of parts. Not like everything would be merged in single part, but can you identify, can you merge 2 3 parts together? And the driver for that is like to reduce manufacturing operation, and also when these parts are being basically manufactured separately, they would have certain joint to basically create that assembly. So if you create a single part, that loss of strength due to joint is reduced, and you can actually save certain material. So with that was the main driver for this particular part merging process. So when we looked at this process, we basically identified like what all different type of joints can happen, how we will automate. But through this analysis, we found like automation of these parts would not be feasible, because there were so many complex cases, and then it was not possible to find a good manufacturable solution for every single case. So we were about to, we were not able to proceed on that. But then we went back to the users and we asked them like, okay, this is what you do. But when we are talking about these pairs or group of parts, how do you actually identify those parts? And there we understood like the assembly could have about 100 200 odd parts, and they end up basically matching the parts, trying to find like which parts potentially they can merge. So we suggested them like, if you are not able to merge the full part, can we look at it differently? Like, can we have a utility to analyze this assembly to identify the merge candidates. And this is what we proposed and developed. So the utility that we proposed, basically it analyzes the merge pairs on various parameters like sheet metal parts having exactly similar material combination, very similar thickness, and a gap of say certain distance. So let's say the two part may not be exactly touching, but let's say there is just 1 mm gap. Still, they may be good candidate for merging. So with these criteria, we analyze this particular assembly, and we are able to identify, present those merge pairs, and then based user can actually review those and mark certain pairs like, okay, these are the pairs I'm going to merge. So their earlier process, which was to identify these merge pairs, is completely, we have a utility to handle that. So the outcome of this was like earlier this merge identification, which used to take 1 or 2 days for assembly of about 100, 200 odd parts. So this came down to about 1 hour. This is one major benefit. And if you but this was relatively small part of the process. Sorry, this was one part of the process. So if we address this, what we observed was like overall merge process speeds up by about 1.5 times. So if you there is still a benefit, right? If you look at the original problem statement, if we and as we understood the complete process and tried to find some other opportunity. So that is the point I would like to emphasize through this case. Like if we understand the full process, perhaps we would be able to identify some even better opportunities rather than hanging on just 1 or 2 things which might have come as a first proposal. So this was the first case I would like to present. The second is interesting. Second case is actually far more complex. We implemented it over longer duration, and this is actually a good example of the 2 points which we talked about. First one is user's intent, and second is front loading the validation. I will talk like how we exactly did that. So this is about hydraulic manifold. So before going in actual process, I'll talk a little bit about this component. So this component is part of aerospace controls. Typically, you have those flight wings. So if you want to, which certain part of those wings would be moving during takeoff and landing. And to control those portions, there is complex hydraulic system, and that whole hydraulic circuitry is fed in a single component to which is called a manifold. So this manifold, I would say it's more like your PCB design, where there is very complex circuit which you are trying to fit in very small space. So that is the hydraulic manifold. The existing process for this was like for the oil, this hydraulic manifold, basically the oil flows through this manifold, and then the holes are defined, and then they are joined together to create one flow path. So the existing process was like there were holes which were defined by a feature template with start and end point. So there was certain level of user intent or automation already present, but it was not completely sufficient. For example, if I look at this right side picture where there is green hole sequence, and that need to be connected. But when the engineers would define the holes, they would define those individually, and then they will have to keep on checking the connectivity. Like if I move certain point, I will have to ensure that the other hole is also moved so that the oil, the two holes are connected and oil is indeed going to flow through that path. And they also need to ensure that the wall thickness they assign to these particular features is also similar. And then final process was like weight evaluation, because this is a aerospace component. Weight was most critical for them, but the weight they would know only after manufacturing decides like how much material they are going to cut. So again, to give an idea, like if you look at the left side picture, which is photo of actual component, so you'll see like the material has been cut at so many places just to reduce the weight. So whatever material is not needed and the manufacturing is able to remove that, they should be removing that. That was the guidance given to manufacturing, and hence this weight evaluation would happen only after the CAM simulation. the weight would not be known. So these were the existing process challenges. So the approach we implemented was quite interesting. We instead of having a single hole, we proposed a composite flow path feature on top of existing hole features. So basically, this whole feature, as it is represented in this box, it has inputs like material, the pressure it is going to carry, the flow rate, etc. And then it also in terms of geometry, it would have input like point 1, point 2. These are like polyline kind of structure, and then in turn the holes would be linked through this. So you will see here, like if the point 2 is changing, it is going to automatically move the hole 1 and hole 2. User the engineer doesn't have to worry about it. And then on that we actually proposed a rubber banding like approach, wherein I'll run this animation again. If I so you like this, the user starts with a single hole, go on introducing points in between, and then ensure the connectivity. So this is more rubber banding like approach for to manipulate the routing. So this way the connectivity is ensured and it gives a lot more flexibility to the engineer. I'm sorry for that. And then there was this validation, which we talked about, the front load validation, where as the user is moving points or breaking, we had certain background things running, which basically does a distance checking, like whether the two holes are coming too close or whether I will have sufficient gap to ensure that minimum wall thickness so that it will sustain that pressure. So that kind of thing we had implemented. And also there was a weight calculation. So if I know the wall thickness of all these features, I should be able to sum them up and get approximate weight. So what we proposed was like there would be approximate weight which would be available. So if you have certain weight target, you'll at least know like I'm getting closer or I'm going far beyond that, so that you don't have to wait for the CAM simulation to come back and tell you like, hey, this is say 40-50% overweight and you need to read it. So that way the overall the iterations were reduced. So when we implemented this, this particular thing went for about 6 to 8 months, but the outcome were phenomenal. Like the development time, which was originally 20 plus days, that came down to 5 to 6 days. So you can see the large benefit that is accrued because of that. And then the design iterations reduced significantly. So earlier they were taking this whole development time. There were a lot of iterations happening, and those were reduced significantly because you are able to do the evaluation for the performance, for the weight at the design stage itself, and that was the benefit of this. The next case is jet engine design. So this process was basically to define the shape and dimensioning of jet engine core. So this is a mix of analytical and empirical rules, and it also includes certain design synthesis for design, weight, etc. Again, this is aerospace, so weight is most critical over here. So here we implemented the automation in two stages. Level one automation, where we identified and implemented various KB features to represent that shape and dimension of the engine core, and uh, we integrated the existing Excel-based performance evaluation. So this is an interesting case. How do you utilize whatever is readily available instead of trying to do everything from scratch? Uh, so they already had this performance evaluation built in Excel. So we just took that and integrated it so that when the design is updated, the Excel the values are updated to Excel and the performance parameters are presented to the engineer immediately. So that was first level. The second level automation that we proposed and implemented was a batch application to iterate through parameter combination. So this engine design involves again multiple parameters, and then the most of the time the engineers were playing with those parameters to basically find that optimal combination. So we proposed doing a batch application which can run those parameter combinations, of course, with certain limits based on the reasonable combination. And then it basically runs those combination, evaluate performance. And the initial idea was to find one best solution, but that was not very easy because there are various parameters which cannot, evaluation parameters. So eventually we proposed like we'll identify 10 best combinations which will be saved for review and finalizing. So the engineer can review those and then finalize one of those, or decide like I would do little bit of tweaking on that. So the outcome of this was like the engineer's effort was reduced 70 to 80%, which was like very first when we did the KBE thing. And then the second is like turnaround time crash. So here I have again a representation of that where the green boxes are showing actual work and the dotted line is overnight time. So we built that batch automation, which happened overnight, and because of that, your time has reduced from about 1 week to just 1.5 days. Where first day engineer does certain things, and second day, based on whatever combinations are proposed, they would do certain level of tweaking and finalize the design. The next case is little different, I would say, which is related to MRO planning. So here we started with certain requirement. The requirement brief for us was to digitize that aerospace component repair identification and to shorten the lead time as seen by the end customer. So the existing process was like the component that is to be repaired, those were shipped to the MRO hub, which basically does actual repair. So the aerospace, for example, that engine repair facility would take out those components, ship it to some other place which actually specializes in repairing of this component. That place they would check and do the actual repair. The whole thing was manual or visual checking, and the repair would start on approval of code. So we implemented full digitization for this, wherein the defect and repair identification is based on the component scan data. And we implemented this a web-based workflow. So this was not dependent on any CAD. This was completely a web solution. And basically, where that scan data is uploaded and the full report is generated. So the outcome was like this repair identification lead time reduced from weeks to days, and it sometimes it eliminates shipping of component which has only minor defects. So that was another positive outcome of this particular automation. So with that, we basically covered 4 case studies, which would have given you idea about like what principle or what approaches, how we implemented those. And hopefully, if you have questions, we can obviously discuss those later. But let's look at like when we come to actual implementation, what kind of technologies we use and what kind of adoption path we follow. So there are 3 slides which I will talk about. Very first is about technology option. So whenever we want to implement automation, there are many different options that are available. So some cases you can actually go for a completely independent application, which is not dependent on any CAD, which we call as bespoke application. Second could come in form of certain API or SDK based plugin. The third thing could be automation macros, which are typically record and replay kind of macros. And fourth could be, of course, the KBE templates. So these are 4 broad options that we see. So typically, as you go up on this pyramid, your flexibility, as you go down the pyramid, you have more flexibility. You can do so many things with that kind of approach. So depending on what you want to achieve, you may choose the appropriate layer. Another aspect which we need to be aware of this is like the top 2 layers we are talking about, they are more dependent on engineering knowledge, whereas the bottom 2 are more dependent on the programming knowledge. So depending on the skill set and what other possibilities you are seeing, you may choose the right approach. Beyond this, there are some more options that are available. So other approach that we have implemented in some case is like spreadsheet or database kind of approach. So we implemented this where you want to keep your knowledge outside the CAD automation or outside the CAD system. So this is again an interesting case where the rules, formula, the performance evaluation I talked about, that remains in some kind of spreadsheets or database, and CAD just has the parametric model, and we connect the two through some kind of automation program. Uh, the next one is like I would say very hot topic, which is AI/ML based automation. So this is also feasible, and typical use cases we have seen are like some kind of classification, clustering, or some kind of generative design. design assistant, etc. But what we have observed is like this need large volume of data very first to basically train. And quite a few cases, we were not able to proceed. We saw certain challenges because the data itself was not available. And creating that data from scratch may not be an easy task, because that itself would be a humongous effort. So we just need to be aware of that part. And in few cases, we have implemented an interesting approach, which is UI-based automation. So where we try to simulate the data entry or clicks via screen-based automation. So this particular case again can be used to a limited extent if you don't have facility for say the SDK, or you don't want to put that much money, because often these SDKs also have a lot of cost. So if you want to avoid that, we can look at UI automation as a limited solution. Now, when we talk about this technology option, the adoption, so on and so forth, the question would still remain like, how do I uh, adopt this particular thing over the years, if at all I want to use automation? So for that, we have certain ideas which I will talk about. So very first is like let's look at it on a time scale and what kind of driver you would be addressing. So typically what we propose is like very first you should look at some kind of task automation, the repetitive task, the checks, so on and so forth. And here the benefit that you can expect is more in terms of productivity and quality. The second is cycle time reduction, so which is more about workflow automation, which we talked about, like batch automation, so on and so forth. And the third can come in form of design analytics, which is going to give you predictability in your lead time and shorten the design cycles. So any automation, if we implement, if we first look at it as a task automation, once it settles, then we try to do it as a workflow automation, and eventually as a design analytics or more complex single click solution. That way you will be able to basically derive benefits in incremental fashion, but also you'll be able to get more predictable benefit of that, rather than jumping into something very complex and bit unpredictable. Okay, so with that, it brings us to end of this session. I'll quickly summarize whatever we talked about, and then we'll open it for question and answer. So very first, the automations can originate from multiple drivers. We talked about this like QCDI, the quality, cost, delivery time, and innovation. Then we talked about ideas for automation, uh, and uh, and then we talked about the planning, which requires consideration of technology choices and also a view of creating more value out of automation. So that is like overall summary. With that, I would end this session and open for any questions.
Yeah, thank you, Nikhil sir. So if anyone have question, they can type in Q&A box. So I think no question is there. So if anyone have question later on, they can reach Nikhil sir. We will be happy to answer the queries. So thank you, Nikhil sir, again. Thank
Thank
you all
you.
the attendees for
Thank you,
attending
everyone.
the webinar. Sir, one question is coming up from Dhaval Borkar.
Okay.
So do we have any solution on sheet metal stripe layout design?
Uh, Yeah, so see, when we talked about these different ideas, uh, the overall thing is like it's not a ready-made solution for just one thing. We have to look at process and then evolve a solution. So for this strip layout design also, there would be solutions which can be implemented. There are certain automations which are readily available, but they may not meet all the requirements. If we understand little more details, we can definitely propose a solution for this.
Yeah.